Hello, everyone. This is hopefully the final lecture for this class. I don't think that I'll have any trouble getting through the material I want to get through, but we'll see. I had to do a fairly substantive overhaul of the notes. I've uploaded that to Canvas. In preparation for what I'm about to talk about right now. I don't know that I've gone into this level of detail before on this topic. I'm not going to tell you anything you don't already know in terms of theorems that you're currently using, for instance, but I may give you a deeper understanding of it and maybe give you some new computational tools along the way. Be on the lookout over the next couple of days for the final. I'm going to post that. Of course, I'll send a notification out to that end as well. That thing will be due a week after the time that I actually post it. And that will be the last assignment. You're turning in a homework set on Wednesday, but the final will be due probably a week from Wednesdays is my best guess at this point, okay? And in terms of resources that you can use, it'll be very similar to the last exam. And so hopefully you're kind of in a good groove with some of that. Any kind of course-related material, even things like Wolfram Alpha, would be totally acceptable. In fact, you will need Wolfram Alpha on this last exam because some of the computation, once you have things like the cycle index polynomial written down, you are going to need to be aided in actually computing some things. But we'll talk about some by hand techniques in this lecture that should hopefully be useful. Okay, so I want to review the multinomial theorem, and I genuinely mean that this should be a review. I'm hoping that you have seen this at some point in time. I think that you have. I think that you've seen it in this class, in fact. And if you've had probability theory with me this semester, you saw it there as well. The multinomial theorem is highly useful, shows up in a lot of contexts, and the so-called binomial theorem is just a special case of it. And we really should have no problem figuring out what it says and why it's true, given the great depth of enumerative power that we have, lots of formulas that we can draw on and whatnot. Okay, so the best way to see this is to just look at an example, and particularly one that isn't too trivial. So let's look at taking a trinomial, that is a sum of three things, x plus y plus z, and raising that to the fifth power. And the goal is to expand this thing out. Like, what in the world is going on with this thing? Okay, well, first of all, you know that this is going to be x plus y plus z times x plus y plus z. Okay, and I'm just going to write out this thing 5 times. Okay, that's 4, and then one more, x plus y plus z. So the question is, what does a generic term look like in here? Okay, so that is, there's going to be lots of terms, but of course, everything's going to be built from x's, y's, and z's. Okay, and in theory, I could have any number of x's from 0 to 5, any number of y's from 0 to 5, and any number of z's from 0 to 5. So here's the question. Let's just look at a very specific, term. So like, let's say x to the first, y to the second, and z to the second. Okay, what is the coefficient of this thing going to be? Okay, well, let's think about this. What that means is when I was multiplying this out, and you know that when you multiply out these factors, these 5 factors that are sitting here, each term is going to be gotten at by taking something from each one of these factors and multiplying those together. And all told, you have 3 choices for the first factor, 3 for the second, 3 for the third, 3 for the fourth, 3 for the fifth. So you have 3 to the, right, so let me just kind of write this down. So 3 times 3 times 3 times 3 times 3, there's going to be 3 to the 5th total summands, many of which can be combined. Okay, 3 to the 5th total summands, many of which can be combined. For instance, there's going to be lots of ways that you can get x to the first, y squared, and z squared, for instance, right? So if I want to think about what the coefficient of x to the first, y squared, z squared is, I notice that, well, I could take, I could take x from the first term. Okay, I could take x from the first term, and then I could take z from the second term. Okay, and then I could take y, and then z. Or I could take x from the first term. I could take z, y. Okay, see what's going on here? I just need to have all possible ways. And incidentally, I could have taken y from the first term, x from the second term, y, and then z, That would have been an x, 2 y's, and 2 z's. Okay, so this coefficient right here, if you think about it, each one of those contributes a 1 to the coefficient of x to the first, y to the second, z to the second. Okay, so that coefficient right there is going to be the number of ways to arrange x, y, z, z. Okay, because up here this was like an etc., right? There were lots of other things that we had to account for. So in other words, that coefficient comes from basically an arrangement with repetition. Okay, so what do we end up with? Okay, so ... right? So this term right here is going to be, well, how many ways are there to arrange those 5 things? Well, it's going to be 5 factorial over 1 factorial. It's like the Mississippi problem. 1 factorial, 2 factorial, 2 factorial, x to the first, y to the second, z to the square, z to the second, etc. Okay? And you start to notice, you say to yourself, I see what's happening. There was nothing special about x to the first, y to the second, z to the second. I could have looked at anything such that the powers added up to 5, okay? Because after all, I always have to take something from each one of the 5 factors. So the powers all total have to add up to 5, and the aggregate powers have to be 5. So the way that we could write this is it's the sum of what? Let's see, it's going to be, E1 plus E2 plus E3 equals 5, where 1 is equal to or less than EI is less than, it's going to be 0 is equal to or less than EI equal to or less than 5. So I don't have to take an X from any of these, for instance. Take all Y's, I can take all Z's, I can take a combination of just Y's and Z's and leave out the X's entirely. That's our prerogative. So what is this going to be? Well, it's going to be 5 factorial over E1 factorial, E2 factorial, E3 factorial. And then it's going to be X to the E1 times X to the E2. Or sorry, this should be a Y. Should be a Y to the E2, Z to the E3. And of course, there's a notation that we came up with for this. So it's E1 plus E2 plus E3 equals 5. 0 equal to or less than EI equal to or less than 5. And the notation is this. You just go 5. It's kind of like a choose, except there's more than 2, right? There's more than just 2 things in the denominator with the factorial. So what we do is we put 5, E1, comma, E2, comma, E3. And then I'm running out of space here, but this is going to be times X to the E1 times Y to the E2 times z to the e3. And what does the multinomial theorem say in general? Well, it says this. So the multinomial theorem, okay, says that if I have, like, sometimes it's called the R-nomial theorem, R-nomial, okay. If I have like R variables, x1, x2, and I'm adding these things together, x, r, and I raise this to the n power, what's this going to be? Well, it's going to be the sum, right? Same kind of game we just played. E1 plus dot 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 plus ER equals n. 0 equal to or less than EI equal to or less than n. Okay. It's going to be n factorial. I always like to just write these out. I don't like to use that multinomial coefficient notation. I just write it out. N factorial, because it reminds me of where this came from, the arrangement with repetition thing. Okay. N factorial, E1 factorial, E2 factorial, dot, 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 ER factorial. It's going to be x1 to the E1, dot, 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 XR to the ER. And of course, the case R equal to 2 is the so-called binomial theorem, which we already know well. Okay, so the binomial theorem is just a special case of this. You'll have x1 plus x2 raised to the power n is equal to what? Well, let's just write it out. Sum E1 plus E2 equals n. 0 equal to or less than EI equal to or less than n. Okay, it's going to be n factorial over, and here's the funny thing. If I know, look at this. If I know that E1 plus E2 is equal to n, I know what E2 is, right? This guy right here is the same thing as saying that E2 is just n minus E1. And then all I have to do with this second condition right here is just make sure that E1 runs between 0 and n. And then E2 is taken care of automatically. So this is going to be E1 factorial, E1 factorial, and then n minus E1 factorial, x to the E1, x1 to the E1, x2 to the n minus E1. And then we actually realize this is just like, okay, I'm going to go sum E1 going from 0 to n of, hey, that's just n choose E1. And it's going to be x1 to the E1, x2 to the n minus E1. And that's exactly the binomial theorem that we know and love well, okay? Why are we talking about this? Well, because when we go to do the Polya enumeration formula, this multinomial theorem plays a huge role. And it's important as good combinatorialists and probabilists for that matter, and even theoretical computer scientists, to recognize when the multinomial theorem is in play, to see these factorials and recognize, oh man, that's a really complicated looking thing that really isn't that complicated at its core. And so this, you can get some massive simplifications happening if you're really kind of aware of when the multinomial theorem is in play. Okay? All right. So we're going to be using this. We're going to be using this at will when we go to rigorously justify the multinomial theorem. Actually, not to justify the multinomial theorem, but to justify the Polya enumeration formula. We will utilize the multinomial theorem at will. Okay, so one thing that we were looking at was we were saying, hey, whenever I'm in the cycle index polynomial, I just have a bunch of variables that are raised to powers, and the powers tell me how many of a particular cycle type I have for the permutation corresponding to that term. Okay, and we're going to be using that quite a bit. But I thought it would be helpful right here on the front end to see why I'm obsessing about the multinomial theorem. Okay, so it's because of this. Watch. So suppose I had something like, you know, x2 to the third times x4 squared, okay? And maybe just for good measure, we'll do like x1 to the 2 or something like that. Well, we know that in the Polya enumeration formula, what we were asked to do was we were asked to actually plug in x1 equal to, you know, let's do red, green, and blue or something. Red plus green plus blue, okay? X2 was r squared plus g squared plus b squared, and x3 was r cubed plus b cubed plus g cubed. Okay, so what do I get when I do that? Well, look, now we know why the multinomial theorem is going to play a role. Okay, so the reason I showed you the multinomial theorem is it comes into play when we actually have to expand these terms out. Okay, sometimes these things, if you have several of the same type, several permutations that have cycle structures of the same type, you'll have constants out front, but who cares about that? What really matters is this part right here. So we're going to have r plus g plus b squared, okay? Right, I think you see why we are caring about this now, okay? And then what? Well, it's going to be r squared plus g squared plus b squared raised to the third times r cubed plus g cubed plus b cubed raised to the square. Okay, and how am I gonna deal with this? Well, the first thing, okay, so that's a multinomial with just n equal to 2. Okay, so this is going to be the sum. Okay, so let's see here. Let's do like E1, 1 plus E1, 2 plus E1, 3. What do these have to be equal to? Well, they have to be equal to 2, okay? I'm just dealing with the first factor right here, which is a square, okay? And then what's the deal? E1i has to be between 0 and 2 for each one of those. So this is going to be 2 factorial over E1, 1 factorial, E1, 2 factorial, E1, 3 factorial. Okay, and then it's going to be r to the E1, 1, g to the E1, 2, r to the E1, 3. Okay, that's the first factor. Okay, times what? Well, let's look at the second one right here. This one's a little bit more interesting, but it doesn't, look, the fact that those are all squared, you still basically kind of do this the same. You just have to know that you're going to be doubling each one of those powers, but the sum itself is the same, okay? So it's going to be, or it has the same kind of setup. So it's going to be the sum, since this is a second factor that corresponds to, right? So I'm kind of concentrating on these sub-indices right here, yeah? So let's see, it's going to be E2, 1 plus E2, 2 plus E2, 3 equals, okay, so these powers have to add up to what in this case? Well, the powers have to add up to the powers have to add up to 3. Okay. And what's going to happen here? Well, E2I has to be between 0 and 3 for each one of these. And this is going to be 3 factorial over E21 factorial, E22 factorial, E23 factorial. And it's going to be R to the 2 E21 times G to the 2 E22 times R to the 2 E23. Close parentheses. And we have one more term here. Okay, this is getting a little bit boring, but it's just good for us to remind ourselves of these things. Okay, so E31 plus E32 plus E33 has to be what? 2? Okay, and 0 has to be equal to or less than E3I has to be equal to or less than 2. This is going to be 2 factorial over, right, 2 factorial over what? E31 factorial, E32 factorial, E33 factorial. It's going to be R to the what? 3 E31 times G to the 3 E32 times R to the 3 E33. Okay, the reason I'm kind of pushing us through this is because you know, it's about to get a little bit crazy when we actually try to go do this in general. So I just want to make sure that we're comfortable doing this sort of thing. Okay, and if we wanted, we could actually even expand these things out. We would have a horrendous looking sum over various powers of these things, but the power on R would be you would have one power that's like times 1. You have another one that's a multiple of 2, and you have another one that is being multiplied by 3. Okay, when you kind of wrote this out, and you would have a product of a bunch of multinomial coefficients, one coming from that first factor, another coming from that second factor, and a third one coming from that third factor, if we were to multiply this whole thing out. Okay, but we could definitely do that if indeed we really wanted to. All right, so the Polya enumeration formula, which we kind of vaguely justified last time, but not really fully. We did it for like 2 colors, and I just said, hey, this thing can be extended to multiple colors, but it will require the multinomial theorem. Well, we just went through the multinomial theorem. So I really do want to go through this in full-throated detail, just so that we have that under our belts. I think it will benefit you. And I think it's a good place to kind of stop the course. Okay. So basically what we do is we take the cycle index polynomial and we replace each one of the variables x sub I with the sum of the, like if I use variables for the colors, C1 is color 1, C2 is color 2, etc. And I replace x sub I with C1 to the I plus C2 to the I, etc. Then the claim is you can get a pattern inventory, which is gotten at by simply extracting the coefficient with a certain number of C1s, a certain number of C2s, and that will tell you the number of inequivalent colorings with that particular pattern inventory. And we took a peek at the icosahedron last time. Okay. And ended up with this down here. We came up with the cycle index polynomial with the icosahedron before, and we were 5 coloring vertices. And I went over into Wolfram Alpha and did this thing. We were messing around with that. And actually, I kind of wanted to show you this. Actually, I went through, just kind of shows you that I was a little bored at some point. I went through and actually expanded this thing totally. Okay, all 1,820 terms are sitting right here. All 1,820 terms are right there. Okay. Yeah, wow, look at that. I'll just kind of scroll through the whole thing here. I was surprised that it kind of continued to let me do that, but there isn't anything missing there. So for instance, let's just kind of pick one out here so that we can revel in what's going on here. So here's one. See this 6930 right here? Okay. So what this is saying is that here we were coloring vertices of the icosahedron. The number of genuinely distinct under the floating symmetries, because that's what our group was, all possible symmetries of this floating object. The total number of truly distinct colorings that consist of 2 greens, 4 reds, 4 whites, 1 yellow, and 1 blue is 6,930. Okay, so that's amazing that we're able to kind of list that out. Okay, so I wanted you to see that, and maybe what I'll do is I'll take this this link and I'll actually paste it into the notes in class so that you can kind of click on that and go here automatically. It may force you to kind of re-expand this thing, but at least you won't have to type that huge obnoxious thing in that I typed in, okay, up here. But yeah, there it is. All 1,820 terms of this thing sitting right there. Okay, so I will kind of paste this link in there into the notes so that you have access to that. Okay, so what I want to do is kind of carefully go through a proof. So this is going to be the last thing in the course. Okay, and I don't want it to be necessarily example driven the way the first thing was. I want to really give a rigorous proof of this thing. I call it the PEF, the Polya enumeration formula. And then we'll look at an example. I have a 7 bead example that's pulled straight out of the book, sort of interesting, and we'll look at a variation of that the book doesn't talk about, that I think is pretty helpful. Okay, so first I want to develop some notation. Okay, it's just for our convenience. Now remember, we're going to focus on a singular summand. If we can just understand what's going on with a singular summand in the Burnside theorem formula, we can really figure out what's happening. And we fully justified Burnside's theorem. There's no question in our mind that that's true. We went through all the rigorous details of that. Okay, so we can write a term for the cycle index polynomial that corresponds with a summand psi of pi. Remember, psi of pi is defined to be the number of colorings fixed by pi. Okay. So that thing is going to correspond to a term in the cycle index polynomial. And you get it by looking at the cycle structure of the permutation pi. Okay? And I'm going to invent a notation for that term. Okay? And I'm going to call it P sub pi x1 ... through xk. Right? So that is, we have this nice correspondence. And I didn't write equals, notice, because psi of pi is a number, and it's the number of colorings that are fixed by pi. Okay? And P sub pi x1 through xk is a polynomial that represents the cycle structure of pi. One thing that is true, though, is that psi of pi, okay, I probably should have written this in the notes, but psi of pi is actually equal to, now since this thing, P sub pi x1 through xk, if I'm doing m colorings, I have this cycle index term, then really all I have to do to get psi of pi is I have to take P sub pi and I have to replace every single variable. I have to replace it with the number of colors. So xk equals m. Okay, so really what's going on here is I'm just taking p sub pi and I'm plugging m in to every single slot. So that's really the most explicit connection between psi of pi and the cycle index polynomial term corresponding to that. Okay. By Burnside's theorem, we have that the entire cycle index polynomial is just 1 over the size of g, and then you just sum over all permutations, these little cycle index polynomial terms corresponding to that pi. Now, I do want to remind you, just because a lot of students forget this at various points, we're assuming that, you know, when we move to the cycle index polynomial and we start thinking about the cycle structure of the permutation as a counting tool, that we're assuming that there aren't really any special restrictions on the colorings, okay? Like vertices being distinct colors, like we had in some of our, like adjacent vertices being distinct colors as we saw in some of our homework problems. These are totally unrestricted colorings. Just going to any vertex and coloring it any color, all right? So, just so you know, because when you start thinking about, you know, one vertex cycling into another one, all of that stuff kind of eliminates the possibility of putting any really specific restrictions on it, like what we had in some of our homework problems. So for those, you would just have to resort to using Burnside's theorem directly. Okay. So let's look at a practical illustration of those summands up here in this formula 7. And let's think about the symmetries of the cube. Okay, so I actually drew a little picture of these things. So I have the opposite facial rotations, and I'm going to do clockwise rotations. So A goes to D, goes to C, goes to B. You know, E goes to H, goes to F, goes to E, goes to H, goes to G, goes to F. Those things are going to be in a little 4-cycle structure. And then I have the opposite vertex rotation as well. Okay, so I drew that axis through A and H. So that means that D is going to go to B, which is going to go to F. Those, right, you have that 3-legged spider right there. Those legs are rotating into one another. D goes to B, goes to F. And on the other side, so I'm rotating like clockwise around that vertex. On the other side, what's going to happen? C goes to G, goes to E. Okay. So you have 2 1 cycles in that case and 2 3 cycles. Okay. So what do we have? Yeah. Okay. So the facial rotation, you know, which 90-degree opposite facial rotation, a row of ADCB. You just have that little 4-cycle and then another 4-cycle. Then P sub that permutation, you have 4 variables here is what you're going to need. You don't have anything beyond a 4-cycle for symmetries of the cube. It's just going to be x4 squared. And then the 120-degree opposite vertex rotation row sub A. Okay, so A and H are going to be in a little, the way I labeled it down there, A and H are in 1 cycles. BFD, CGE, those little 3 cycles. So you get x1 squared and x3 squared as the term corresponding to that. Okay. So this notation gives us a way to kind of go back and forth between terms of the cycle index polynomial and individual permutations. I don't know why, but the book never actually does that. They just kind of use this ad hoc approach all the time. So I think it's pretty helpful to have this particular notation in our back pockets. And it's going to help us really understand why the Polya enumeration formula is true. Okay? Just because we want to be as clear with our communication as possible, I'm going to act as if we're always coloring vertices, just so I can refer to vertices. You know, it doesn't have to be vertices, could be edges or faces, but I'm just always going to talk about vertices. And again, that doesn't really destroy generality at all. Okay. So again, we're looking at a single generic summand in the cycle index polynomial corresponding to permutation pi, and I'm just going to write it as x1 to the a1 times all the way up to xk to the ak, which means a1 1 cycles and ak k cycles. Okay. Then if n is my number of vertices, then you know that n has to be equal to 1 times a1 plus 2 times a2, because each one of those a2 2 cycles consists of 2 elements, right? Plus all the way up to k times ak. So the number of vertices is equal to that sum. Okay. Okay. So once again, I just want to remind you we're considering coloring vertices freely, so no special restrictions with M colors. And I'm going to use C1 through CM the way they did in the PEF statement upstairs to denote our M colors. Okay. So just focusing on that one term piece of pi from the cycle index polynomial corresponding to pi, this is the question we need to answer. The question is, how many of these M colorings are fixed by pi specifically, and have, because I'm interested in a pattern inventory when I'm talking about Polya enumeration, have B1 vertices colored color C1, B2 vertices colored color C2, etc., BM vertices colored CM. Of course, what has to be true about those B sub i's? Well, when I add them together, I better get all the vertices. So B1 plus B2 plus etc. plus BM is equal to N. Okay. So here is where we're going to start counting stuff. Okay. And it ought to remind you of what we did in the case of just 2 colors, but you're going to notice that it starts to feel very multinomial-esque pretty quickly. Okay, so this paragraph right here that we're about to read and the next are really the key to understanding everything. So just try to understand what's happening in these 2 paragraphs. So in order to color B1 vertices with color C1, okay, because that's what we wanted to do, B1 vertices with color C1, we need to choose some number of 1 cycles, okay? Okay, so to color C1, all right? So some number of 1 cycles, and I'm going to call that N11, okay? N11. So N11, 1 cycles are going to get colored C1, okay? Some number of 2 cycles, we'll call that N12, since we're talking about color 1 this entire time, okay? And remember, we want B1 vertices total to get color C1. Okay, so we're going to select N1, comma 2, 2 cycles to get color C2. All right, and now remember, if we choose that many 2 cycles, each one of those 2 cycles, the 2 vertices in that cycle are going to both get that color C1. Yeah. Okay. So that's going to account for 2 vertices. Each 2 cycle accounts for 2 vertices, where each 1 cycle accounted for 1 vertex of color 1. And we're only talking about color 1 right now. We want B1 total vertices to get this color. Okay, etc. We go all the way up to the K cycles. We'll color N1K of the K cycles color C1. Now notice that each one of those K cycles is going to account for K vertices. Okay. So what has to be true? Well, B1, the total number of vertices, needs to be equal to the number of 1 cycles plus 2 times the number of 2 cycles that I chose, plus etc., plus K times the number of K cycles that I chose. Because when I color those with color C1, I have to color them all with color C1, anything in one of those cycles. Okay. So what's the total number of ways to do this first step? Well, from the A1 1 cycles, I have to choose N11 1 cycles, okay? And then I go to the 2 cycles and I choose N12 2 cycles, etc., etc. Then I go to the K cycles, there are AK of them, and I choose N1K of them. And I'm telling you that last equality right here is just me writing out the formula in terms of factorials. A1 factorial dot 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 through a k factorial upstairs. I have a bunch of n1 1 factorial dot 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 n1 k factorial, and then of course I have a1 minus those things factorial, or ai minus those things factorial downstairs also. Okay. So what next? What next? Well, now we're going to move on to color 2. We have our B1 vertices of color 1, but look, one thing I will point out at this point, I could have, I chose N11 of 1 cycles, N12 2 cycles, etc. I could have done different N values, yeah? Could have done different N values, but that's going to be involved in a sum that we do later on, and then that's going to really start looking like multinomial stuff does. Okay, so I just said some number of 1 cycle, some number of 2 cycles, but overall I'm going to have to sum these things together later. Okay, all these different cases for different N sub 1 comma i's. Okay, so what about B2 vertices of color C2? Well, first we have to choose some number of 1 cycles, okay? And 2 1, since we're dealing with color 2 now. But you have to choose them from the remaining 1 cycles, okay? And there are A1 minus N1 1 cycles. We color those C2. Okay, some number of 2 cycles, we call that N22 to color C2. And remember, again, it's going to be from the remaining, which is A2 minus N1 2. Etc. Some number of k cycles in 2k to color 2. And these choices are all done from the cycles that remain after the first step. Okay? And of course, what has to be true? Well, the total number of vertices that are being colored, B2, has to be the number of 1 cycles plus twice the number of 2 cycles plus etc. plus k times the number of k cycles. That's the total number of vertices that are being accounted for. You color 1 vertex in a k cycle, a certain color, in this case, color 2. You have to color them all that color, because remember, we're concerned about fixing stuff. Okay? And so the total number of ways to do this step after the first step is, okay, basically all I did was transfer this guy right there. Okay, and then what I did is I just wrote down all of the chooses again. This first thing is just like A1 minus N11 choose N21, and I just wrote out the factorials. And one thing you might notice pretty quickly, if you're paying attention here, is that you get some nice cancellation. A1 minus N11 factorial, that cancels that, right? All of this stuff is going to cancel. AK minus N1k factorial. So all those things go away, and what survives are these, these n's, these various n's, and the A1 minus, now I have to subtract 2 things away. All of those things survive. Okay, so this is the new formula that you get right here, right here. Okay. And I think that you start to see a pattern emerging. The numerator seems to be staying the same, but the denominator is getting more and more robust with each step. And the A1 minus things, eventually that's going to just decrease down to 0, okay? 0 factorial. And you're just going to get all these like n's down here. And remember, I could have done different n's, but that will be handled via a sum later on. Could have done different n's because I just arbitrarily decided, I don't know, N21, N22, etc. But those could have been different values of n. Okay. So, oops, C. We were right here after the second step. And now I'm telling you we're getting close to being done. So continuing in this way, we eventually arrive at that formula. Okay, so the N1, comma, whatevers, those come from the color 1, the first step. The N2 whatevers come from color 2, the second step, etc. The NM whatevers come from the mth step corresponding to color M. And we have all of these identities that have to be satisfied. So for instance, What has to be true if I were to add N11 and N21 and NM1 together, okay? Well, those have to account for all the 1 cycles. The second number is talking about which cycles I'm choosing from, okay? So those have to account for all of the A's, right? So this and this, right? Those N1 whatevers, those have to total up to A1, okay? Which is what I'm saying right here, okay? So AJ, N1J plus N2J plus et cetera plus NMJ, all of those have to add up to, those have to account for all the J cycles. Okay, the second index is talking about the which cycle you're talking about. The first number is which color you're talking about. Okay. All right. So that goes J going from 1 to K. And then what about the B's? Well, the B's, okay, if I'm on a fixed I, like the first number, so I'm talking about color I, well, that we already said that, you know, the number that I select from the first, from the 1 cycles, plus 2 times the number I select from the second, from the 2 cycles, plus all the way up to K times the number I select from the K cycles, that has to be the total number of vertices I wanted to be of color I, okay? Right, so BI is the number I wanted of color I, okay? Then, so this right here, look at it, that's just a product of a bunch of multinomial coefficients, isn't it? It's a product of a bunch of multinomial coefficients. And it looks like what I've done is just take various values of those n's. There's a product of a bunch of multinomial coefficients, and there's going to be some kind of sum involved over various values of those n's. Oh, and by the way, down here, I thought it was kind of nice to have this little tabular rendering of how the B's and A's and N's all relate to one another. Okay, so B1 is equal to that, B2 is equal to that, etc. But then if I add up all the B's, I get the total number of vertices. And of course, if I add all these things together, I get A1. If I add all these together, I get 2A2 because they're all multiplied by 2, etc. If I add up all the K's together, or the K in 1K, K in 2K, etc., I get KAK. Yeah? And of course, we already knew that that was equal to N before, right? The number of 1 cycles, remember A1 is the number of 1 cycles in this term of the cycle index polynomial, plus 2 times the number of 2 cycles, plus et cetera, plus K times the number of K cycles has to be the total number of vertices. Yeah. Okay. So this final product right here, this is what I'm kind of saying, this final product in 8, okay, which is that, is just a product of multinomial coefficients. Yeah, okay. And I'm not going to go into a ton of detail here, but you just believe it now that that if you go down here and you say, well, what if I wanted the coefficient of C1 to the B1 all the way through Cm to the Bm? I'm telling you, if you plug in x1 equal to C1 plus C2 plus et cetera plus Cm raised to the A1, remember the term was just x1 to the A1, x2 to the A2, and I'm replacing it by what the Polya enumeration formula said to do. I'm telling you, you're going to get exactly something that looks like that when you expand this thing out. Okay, it's a little bit nasty, but you end up getting exactly that. You get a whole bunch of CIs raised to various things, and you can literally replace them by the B's that we have in our formula, and it works out real nice. Okay. This notation right here means coefficient of C1 to the B1, etc. Okay, because that's going to be basically our variables. There you go. That's it. So if you sum all of those together, in Burnside, because remember that was just for a single permutation. So you sum all those together for various permutations. And remember, we always divide by the size of the group to account for the symmetries, right? Because everything gets counted size of G times, okay? And then you divide by that to kind of divide out by the symmetries. That's what Burnside's theorem is all about. You get the total number of G and equivalent M colorings with B1 vertices colored C1, et cetera, all the way to BM vertices colored CM, being given by just that formula right there. Coefficient of C1 to the B1, all the way up to CM to the BM. The cycle index polynomial with various x's replaced by those corresponding sums of variables involving color variables. That's the PEF. And I'm not going to go through and actually multiply all this out, but I would challenge you to do it. And I promise when you do it, you end up with things that look like this, okay? The multinomial coefficients. Okay, all of the data is up there in order to kind of follow through on that, but it does get a little bit fierce. So I just wanted to give you kind of a high view of what's going on here, drill down a little bit more so that we get it a little bit deeper. Hopefully this stuff makes a little bit better sense. Okay, I just want to remark on a couple of things. So first of all, extracting the desired coefficients in the PEF pattern inventory can be really a bear, right? I mean, we did the icosahedron example, and I don't know that it really would have been possible to do a lot of those things as a human being by hand unless it was very easy, like a number of colorings that have all yellow vertices or something, okay? So Wolfram Alpha is going to become a good friend, or any kind of computer algebra system like Maple. It's helpful, and I'll allow you to use that, even if it's a simple situation. But if it is a simple situation, it is useful to be able to do those things by hand, okay? I mean, just to remind you of how some of these things are working. So I wanted to kind of finish by looking at an example that's in the book, okay? So example 2 in the textbook is this. It's like 7 beads. Okay, it's a 7 bead example of just black and white beads only. Okay, and we're only looking at rotations first. Okay, we're only looking at rotations. Okay, so so we have this necklace. Okay. Okay, so here's this. Right, so here's this 7 bead necklace, right? Okay. So what are we going to have for our group in this particular case? Well, we're going to have 0 degree rotation. So we're going to have some weird degreed rotation here, okay? So I'll just call it rho, okay? And then basically rho squared, okay, which is rho composed with itself. Okay, and we'll say rho cubed, rho to the 4th. Okay, so this going from here to here, that's rho, right? Rho to the 4th, rho to the 5th, rho to the 6th. Okay, and incidentally, you know, rho squared means this. So it's like rho, okay, etc. And then rho to the 7th is just 0 degrees again, okay? Now, what's interesting here is, could there potentially be any breakdown in cycle structure? I mean, it's pretty clear that if I were to compute, for instance, like P sub rho of, you know, X, let's see here, X1, I think we're going to need a 1 cycle for the identity. I going to need any 2 cycles? I don't think so. I think at most you're going to need, so 1, 2, 3, 4, 5. So there's going to be 7. Okay. And that thing is going to be raised to the first power. Okay. So what am I going to get here? So for rho, it's just going to be, it's just a 7 cycle, and that's it. Okay, to the first power. That's it. And incidentally, that's also going to be true for any of these rho to the I, x1, x7. And that's for 1 less than or equal to I less than or equal to 6. Okay, and what's p of 0 degrees, x1, x7? Well, it's going to be x1. It's going to be a bunch of 1 cycles, okay? So what are we going to get for the cycle index polynomial? PG, x1, x7, okay? Well, it's going to be a 7th, so we have to take care of our symmetries by dividing by the size of the group. And then what's it going to be? Well, it's going to be x1 to the 7th. Then I have a whole bunch of these x7 terms. How many of them? Well, 6 plus 6, x7. Okay, now we're going to use this. We're going to use this to actually get what we want here. Okay, shifted down here just slightly. So what's going to happen with this? Well, I wanted the number of 3 black and 4 white bead situations. So I want the coefficient of b to the 3rd, w to the 7th of the cycle index polynomial. x1 is going to be b plus w. What about x to the 7 or x sub 7? That's b to the 7 plus w to the 7. That's what we replaced that with. Okay, so that's going to be a 7th, 1/7. Okay, let's think about this. It's going to be b plus w to the 7th plus 6 b to the 7th. Right, x7 is just b to the 7th plus w to the 7th. Close parentheses. Okay. Well, what is the coefficient of b to the 3rd, w to the 7th of that? Well, I mean, one thing that I would point out is that b to the 3rd, w to the 7th. Okay. What about the what about the 6 times the quantity b to the 7th plus w to the 7th? Does that contribute at all to the coefficient of b to the 3rd, w to the 7th? Well, no, that w to the 7th sitting right there doesn't have a b to the 3rd multiplied by it. So this guy right here does not contribute. That does not contribute. Okay. So what is the coefficient of this thing? Well, it's going to be 1/7 times something. For this guy right here, we have to use the binomial theorem. Okay, we can actually do this by hand. Okay, so what is the coefficient of b to the 3rd, w to the 7th? Wasn't that going to be 7 choose 3? Okay, and then there's the 7 choose 3, and then it would be b to the 3rd, w to the 7th. Right, so that's what we get as the coefficient of this thing. The 1/7 came from there, right? And we don't write b to the 3rd, w to the 7th because I already said I want the coefficient. That's what that notation means. The coefficient of b to the 3rd, w to the 7th, and that is 7 choose 3. I multiply that by 1/7, and that is the answer. I didn't have to do any kind of weird Wolfram alpha magic or anything like that to pull that off. Okay. All right, so it's 1/7 times 7 choose 3. And I ask an additional question here, a little follow-up. I say, how would things change if we allowed, okay, how would things change if we allowed the necklace to float? That is, we allowed the thing to reflect also, okay? So we had the, we had the 7 beads. Okay, so there we go. Okay, so like this. Okay, so first of all, what is our group going to be now? Well, 0 degrees, we'll go with rho. We still have the rotations. Rho squared, rho cubed, rho to the 4th. Again, I am going to label these things. Okay, so I'll say A, B, C, D, E, F, G. Okay, and rho is doing this. And of course, rho squared takes A to C, etc. So this is rho squared. Okay. And again, all of these rotations don't break down into smaller parts because that would imply a factor of 7, and 7's prime. Okay, so there's no breakdown like that. Kind of like what we had in the case of the square, where 180-degree rotation gave us 2 cycles. Yes, that's because 4 is equal to 2 times 2, so it does break down. The 7's prime. Okay, so and then I have rho to the 6th. All right, so what about reflections? Okay, well, there are several reflections that we can have here. So there's a reflection through A that goes to the opposite side. There's a reflection through B that goes to the opposite side. Okay, you can kind of see that that's a mirror image on either side of that, etc. Okay, so let's write those down. Okay. So I'm going to write that as R, so for reflection, A, RB, RC, RD, RE, RF, okay, 1, 2, 3, 4, 5, 6, and RG, okay? And again, that's all possible. Like this, we can kind of think of this necklace as kind of like a 7-gon, right? And we know the total number of destinations for a vertex was 7, and then an edge on either side of that. There were 2 options for that. So the maximum number of symmetries, 14. We just found 14 of these. Okay, what is the cycle index polynomial for this beast? Well, oops, let me, well, I'll write PG, that's fine. So what variables are we going to need here? Well, it looks like we're going to need to have an x2 now because we're going to have some 2 cycles coming from each one of those reflections, right? Because you're going to have, like, for instance, the one going through, the reflection going through A, B, and G are in a 2 cycle, C and F, D and E. So it looks like a bunch of three 2 cycles for each one of those reflections in a 1 cycle, okay? So it's going to be 1/14 over the size of the group. I still have x1 to the 7th plus all of those rotations have the same structure, namely being a 7 cycle. And it's going to be plus 7. All of the reflections have the same structure. What is that structure? Well, it's x1, and then what is the deal going to be? It's going to be x2. Okay, how many 2 cycles? To the 3rd. Okay. And if I wanted the number of these that have 3 black and 4 white beads, oops, I want 4 white beads. Right, 3 black and 4 white beads. Yeah, I think I did that right before. 3 black and 4 white beads. Yes, it was 1/7, 7, choose 3. Yeah, I think that's what I got. I was worried I did hit W to the 7th, but I think I did that rightly. Okay, I think I might have said something about w to the 7th. That's just nonsense. I don't want w to the 7th. I wanted w to the 4th. Okay, so let's see here. I want to know the coefficient of b to the cube, w to the 4th. Maybe I wrote w to the 7th before, so ignore that if I did, and just replace it with w to the 4th. And I want pg of what? Well, it's going to be x1 replaced by b plus w. It's going to be x2 replaced by b squared plus w squared. And it's going to be x7 replaced by b to the 7th plus w to the 7th. Okay. So this is going to be the coefficient of b to the 3rd, w to the 4th of what? 1/14th. And it's going to be b plus w raised to the 7th plus 6 b to the 7th plus w to the 7th. That won't contribute at all. Okay, so plus, what's going to be the deal here? B plus w times, oops, there's a 7 right here. 7b plus w, and then it's going to be b squared plus w squared cubed. All right, so let's think about this. What is going to happen here? So what's this going to be equal to? Well, it's going to be a 14th because of this. Okay, this guy right here doesn't contribute. Okay, there's no b to the 3rd or w to the 4th going on there. Okay. What can I get here? Can I get something from this first summand right here? Well, yes. Again, if I want 3 b's, that's going to be by the binomial theorem, 7 choose 3. Okay. Now, what about this last term right here? Okay. How do I deal with that? Okay, I don't get anything from the b to the 7th plus w to the 7th term, but what about that last one right there? Well, so, I mean, maybe it would be helpful to kind of expand this thing out right here. Okay, so what is that? It's going to be 3 choose 0, right? So 3 choose 0, 3 choose 0, b to the 0, w to the w squared to the 3rd, which is w to the 6th. Okay, so, okay, so let me just do 3 choose 0, w to the 6th plus 3 choose 1, b squared w to the 4th plus 3 choose 1, b to the 4th w squared, or so that's 3 choose 2 actually. Okay, plus 3 choose 3, b to the 6th. Is there one of these that actually is going to contribute? Now remember, I want the coefficient of b cubed, and I think that the answer is yes. It's this one right here. That term right there is actually what I need, and it's going to come from when I actually take this b and I distribute it to this thing. If I distribute it to that thing, I'm going to get a b cubed w to the 4th, but that's the only way I can get that, and that's going to be multiplied by 7, right? So in the end, what do we get here? We get a plus 7 times what? Plus 7 times, I don't think, there's no way I can get anything else other than just by distributing that b to that term specifically. Nothing else works. All the rest of them either don't have enough b's or don't have enough w's, or don't have the right number of w's. So it's going to be 7 times 3 choose 1. Okay. So there you go. That's it. Okay. 1/14 times the sum of those two things. So that's very interesting, okay? That is going to be the number of things that actually have 3 blacks and 4 whites. And we were able to pull that off without resorting to some kind of usage of a computer algebra system. I'm pretty sure that before this example, the one before that I had w to the 7th in there, but I think I did write down the correct answer. So just make sure to insert that little mental correction as you watch that again, okay? All right, everyone. I think I'm going to leave it at that. I would really encourage you to go up and try to expand that thing using the multinomial theorem and just make sure that those counts match up. I promise that they do. It's a really sort of an interesting result. It's a nice utilization of multinomial theorem. And it's a nice climax to the course, being able to count things that are so complicated. Really enjoyed the course. Hope you did as well. Enjoyed teaching it, even in this weird format that we've been doing for the last few weeks. I would encourage you to go fill out the course evaluations. I know it was a weird semester, but go do that anyway. I'm always eager to get feedback. I will change a couple of tweaks in here that I mentioned as I was going through this, but I'll re-upload the notes again as in a fully final form, and be on the lookout for that final. Okay, be sure to come and ask questions during class time or office hours, should they arise. Enjoyed teaching you guys. Hope to see you around in the fall, okay? Thank you very much for taking the course. Appreciate you guys.